Kimi has introduced K3, a model built with 2.8 trillion parameters. While frontier performance has typically been the domain of closed, proprietary models, K3 is an open release that reports benchmark parity with flagships like GPT-5.6 Sol. This chart displays performance on Terminal Bench 2.1. Kimi K3 reaches a score of 88.3, placing it ahead of GPT-5.6 Sol and Claude Opus 4.8. That trend continues in the DeepSearchQA evaluation, where the model achieves an F1 score of 95.0. The weights for this 2.8 trillion parameter model are scheduled for public release on July 27, 2026. Beyond the raw capabilities measured by these benchmarks, the pricing model for K3 deviates from the standard costs associated with frontier-scale intelligence. The model supports a 1 million token context window, served at $3 per million input tokens. To understand how a model of this size can be served at a commodity price point, we have to examine the specific engineering choices in its architecture. Kimi K3 represents both a development in algorithmic scaling and a change in the economic baseline for high-parameter AI models. Large models generally route data through vast layers of artificial neurons to process information. For models exceeding 1 trillion parameters, a mixture of experts architecture divides the network into specialized subnetworks, ensuring only a portion of the model is active at any time. This graph represents the internal structure of Kimi K3, which contains 896 distinct expert nodes. K3 utilizes a framework called Stable LatentMoE. For every token processed, the system activates exactly 16 out of the 896 experts. This activation ratio is significantly more sparse than existing industry standards, which typically use a much larger percentage of their total parameters per token. By maintaining 880 experts in a dormant state for each calculation, the model reduces the active computational work required for inference. This design results in a 2.5-fold improvement in scaling efficiency compared to the previous Kimi K2 model. Extreme sparsity serves as the mechanism that makes a 2.8 trillion parameter model functional without requiring an impractical amount of hardware power. While routing handles the model's size, managing a 1 million token sequence creates a separate challenge for memory management. Standard attention mechanisms accumulate data uniformly as the sequence length grows, which creates a computational bottleneck in large context windows. K3 addresses this by using Kimi delta attention and attention residuals. Instead of accumulating every data point, the model selectively retrieves representations across the network depth. This selective retrieval allows the model to maintain the integrity of a million-token sequence without the memory state becoming overloaded. Kimi delta attention does present challenges for standard prefix caching methods used during inference. To solve this, the Kimi team developed a custom prefill cache implementation and released it to the VLLM open source community. KDA provides the framework necessary to enable long context reasoning at scale, moving the architecture past the limitations of traditional attention. Managing 896 experts also creates bottlenecks during the training phase, specifically in how data is routed between them. At this scale, standard routing methods often fail. This graph shows the resulting expert imbalance, where some nodes are overloaded while others crash. K3 uses Quantile Balancing to stabilize this process. This method derives expert allocation directly from router score quantiles. It uses a calculated distribution rather than relying on heuristic guesses. By automating this allocation, the team eliminated the need for sensitive balancing hyperparameters that typically require constant adjustment during training. Moving away from heuristics to quantile balancing is what allows a 3 trillion class model to remain stable throughout its training cycle. The final component of the $3 pricing model is the way the software interacts with physical hardware. K3 uses quantization-aware training, applying compression techniques directly during the supervised fine-tuning stage. This matrix shows the model's weight footprint. These weights are compressed into the MX-FP4 format. Simultaneously, the model activations are compressed into MX-FP8. This level of quantization reduces the memory bandwidth required to serve the model, allowing the 2.8 trillion parameter architecture to function across standard hardware configurations. While this compression improves efficiency, Deploying K3 still requires supernode configurations with at least 64 accelerators to maintain high-bandwidth communication. The combination of these software and hardware optimizations is what makes the $3 per million token rate a technical reality. When viewed as a single system, Kimi K3 shows how complex software can be optimized to fit within existing infrastructure. The system is built on 3 technical pillars: high-sparsity expert routing, quantile balancing, and MXFP4 quantization. These mechanisms have enabled an open model to match the performance of proprietary flagships on major benchmarks. The prevailing assumption has been that 3 trillion class models required a level of capital and proprietary technology that few could access. By releasing the weights and lowering the unit cost of input, K3 lowers the barrier to entry for high-parameter intelligence. With these capabilities becoming openly available, the primary competitive advantage for AI developers is shifting away from model architecture. If frontier intelligence is now an open commodity, we have to determine where the next layer of value will accrue in the technology ecosystem.